Scusami, mi hai detto che l'hanno chiuso, quindi non parlo. Gliel'hai detto alla master. No, glielo dico io. Right.
There we go. Now I should. Yeah, now it works.
Okay,
It has to be.
Okay.
One thing though, I'm gonna have to jump. I'm gonna have to jump. So maybe if I have an arrow, turn an arrow, like a point. Or I could do this.
If you want to screen,
Or actually, I just want to be able to like jump ahead, but I can just scroll ahead. So that's fine. Yeah. So why don't we do this, and then I can just jump ahead like this. Yeah, that's fine. Because I'm actually going to be in the middle, but I want to show this.
Okay.
Yeah. Let's see. We'll see if we'll see how it goes. Yeah.
So, good afternoon. Yeah, my name is Simon Carrara. I'm part of this department, and on behalf of the chair of our department, Professor Guido Busto, welcome to everybody here in the Sala del Pico, that is the main important room of our department. As you know, this workshop, the Replicability Climate Science, is a sort of public event connected with our summer school, that is a 1 week summer school on the same topic. And so I take this occasion that I have a microphone to just to thank my colleagues that organized this workshop and the summer school. It was very hard work, and it was an artwork that was done by Bruno Scarpa, Alessandro Salvanda, Fabio Gigenti, and me. But then there are also the instructors of that teach during the afternoon time. That is Gianfranco Toet and Filippo. So thanks to all, but also thanks to the administrative staff of our department, the statistics department, and our department to, let's say, help us in this hard work. And of course, thanks to the two main lecturers of our, let's say, summer school and our now workshop, that is Brandon Fidelson and Giovanni. It's a great pleasure for us to be here and also in this book. I think that it could be a very good occasion to, let's say, talk about the community crisis in a, let's say, large public debate. And so I don't want to take more time and just to thank the first speaker, that is Frank Person, that we speak of the education crisis, the view from the other side. Thank you.
Thank you so much. I want to thank all the organizers for making this happen. This is a very rare and special event. I attend a lot of events, and this is really unique because it involves, well, first, a really important problem that we face. But the way it's been organized is just wonderful. We have a really diverse group of students in philosophy and statistics, and this kind of problem requires an interdisciplinary work. And so having that opportunity to speak to an interdisciplinary group of students, they're going to be the ones that have to deal with this problem. They're going to be the ones that hopefully work together to help make this better. So it's just a privilege to be here and to be part of this program. So thank you so much for including me. The lecture I'm going to give is part of a series of lectures that I gave to the students in the last 2 mornings. And if you're interested in getting a full copy of all the slides, you can point your phone at one or both of the barcodes there. And there's a version that's 1 slide per page, and there's a version that's 4 slides per page. If you're interested, I thought I would just put that up for a few seconds before I start, because I'm actually going to jump into the middle. You know, this was 4 hours of material that we've been presenting to the students, and I'm just going to do a little slice of it in the middle there. So yeah, thanks so much for coming. It's this is such a wonderful room and just a beautiful university and the city, and everyone here has been so nice and supportive. I'm just very grateful to be here. So what I'm going to focus on is really 2 things. First, I'm going to focus on why we think there's a problem. So there's supposedly this crisis. Well, what is it? Why do we think there's a crisis? You know, what's the evidence for the existence of this crisis? That's what I'm going to talk about first. And then I'll talk about some possible explanations for why the crisis exists. How did it happen? How did we get here? So first part, where are we? What is the crisis? What is the evidence that there is a crisis? And then what are some of the explanations for why we find ourselves in such a situation? And I hope I'm not, am I blocking this? Should I say more? Sorry. Okay. So the evidence for the crisis, or the reasons to think there's a crisis, actually go all the way back to the 1970s. And I'll come back to that, but I'm going to jump into the middle of the history here. And one thing that happened, this is mainly, I'm going to talk about psychology, research in psychology and behavioral science and social science, mainly what I'm going to focus on. And one thing that was noticed, you know, back in the 80s and the 90s and more recently, is that there was a preponderance of positive results or significant results being reported in the psychological literature. Pretty much the vast majority of results were positive, and you see a much smaller percentage of negative results. And so that was these are just some studies that sort of give us reason to think that we shouldn't expect to see so many positive results. We shouldn't expect to see as many positive results as we are seeing. And so that's what these studies are about. And that was a source of concern. Okay, so we're seeing all these positive results, very few negative or insignificant results in psychology. And that was, okay, so that was kind of a red flag that something was wrong. And later, though, that concern was confirmed when people tried to actually replicate or reproduce the results from earlier psychological studies and studies in other fields, but I'll focus mainly on psychology. So there were some high-profile cases of individual studies that seemed questionable. For instance, there was an ESP study that was done that claimed to provide positive evidence that some people can feel the future. Okay, and this was published in a major psychology journal. So that was alarming. That was a little bit alarming. And along came the open science collaboration. Brian Nosek is a psychologist who got very interested in trying to replicate, trying to reproduce the results of some of these psychological experiments. And so what he and his team did was they looked at 100 contemporary psychology experiments, 97 of which claimed positive results, and only 3 had negative results. And their attempt to replicate only allowed them to replicate or reproduce the results of like 1/3 of the studies. So maybe 30% or something of the studies seemed to replicate. Also around that same time, or maybe a little earlier, scientists in some of the biotech and pharma companies were realizing that very few of the experiments in the areas that they were interested in were replicated. Maybe 20% were replicated. And similar kind of meta studies have been performed in other fields. So that's when we really started to believe that there's a crisis. We have a preponderance of positive results, very few negative results, and when you try to reproduce the positive results, a pretty small percentage of them were actually successfully able to be reproduced or replicated by other researchers. So now, that's why we think there's a crisis. We've got a widespread failure of replication in the behavioral sciences. We already knew there were too many positive results, and I'll talk again about that more later. So now I want to shift gears and think about, well, why? What's the explanation? Why did this happen? And well, there's 2 kinds of explanations that I'm going to talk about. One is what I'll call a proximal explanation. Those are kind of the immediate causes of the crisis. And then there's more distal causes of the causes, if you will. So I'm going to talk about both of those. Okay, so I'm going to get fraud and that right out of the way, because I hate fraud and I don't want to talk about fraud. So, but let me just say, yes, in some individual cases, there's fraud. I think it's a very low percentage of cases. I think most scientists really want to understand the world, and they're trying to do their best to understand the world better. But there are some high-profile cases lately of fraud. The president of Stanford recently resigned and retracted some papers. There are 2 very famous, ironically, honesty researchers who had to retract some of their work because of allegations of fraud. That's an unfortunate irony in all of this. The honesty researchers don't seem to be honest themselves. Okay, but I think that's less than 10% of the cases, and I'll provide some evidence for that later. So I don't think that's a major driver of the problem. It's there, but it's not going to really explain the bulk of the crisis. So what is going to explain the 90%, say at least, that's not due to fraud, it's due to other causes? I'm going to focus on what I'm going to call questionable research and publication practices. And to make things more tractable here, to make it simpler, I'm just going to focus on trying to explain why there might be such a preponderance of positive results in the literature. How did that happen? Why this skewing towards the positive results and very few negative results? Dorothy Bishop is a psychologist in the UK, and she has this great expression, the four horsemen of the replication crisis. And so she breaks down these causes of the replication crisis into like four categories. So I'm going to kind of use those to frame my discussion today. The first set of causes are what she calls, well, publication bias and also citation bias and spin. So publication bias just has to do with the fact that journals tend to publish fewer studies with negative results for various reasons, maybe some of which I'll talk about later. Negative results just aren't as fun. They're not as interesting. They're not as exciting. They don't really attract the eyeballs, you know, in the way that positive studies do. Citation bias, that's just people tend to cite work that their own work and work that supports work that's like their own work. This is a form of confirmation bias. Human beings tend to be more sensitive to evidence that confirms the views they already have than views that doesn't support the views they already have. And then finally, spin. Spin is when you exaggerate what you've done in your study, in the abstract of your study. Again, that tends to get more eyeballs on it. Makes it more attractive to people because people look at abstracts. And that's okay. So those three things, I'm going to talk about how those interact in a particular case to lead to a preponderance of positive results. That's one set of causes we'll look at, and I'm going to look at particular studies that indicate that. Okay, and then there's a big category called p-hacking and outcome reporting bias. And well, what are these? There's a big category. I'm going to give a list later, but it's a big category, like a laundry list of things that you can do, which will kind of make it not very surprising that you would have found a positive result. And so it makes the fact that you found a positive result less interesting, okay, than it might have otherwise been. Okay, low statistical power. Okay. I may skip that one because that's kind of a technical one. I'm going to skip. I'm actually going to skip that for this audience. That's more of a technical one. I put in that for the students because it involves some probability theory, but I'm actually going to skip that. And then finally, harking. Harking is hypothesizing after results are known. And so here, in the worst case, what happens is you do a big exploratory analysis of a bunch of data, and you find some significant result, which you're bound to do if you look at enough data, okay? And then you kind of write a paper around that as if you always had that as a research question in your mind, and somehow you designed an experiment to test it, but you didn't, you just found it, and then you wrote a paper around it. But there's a kind of inevitability to that, because of course, when you look at enough data, you're gonna find significant results. It's statistical inevitability. Okay, so I'm going to talk about harking too, but I'll skip the PowerPoint. Okay, let's start with publication and citation bias. This goes, now we're back to the 70s, because back in the 70s, people discussed what became known as the file drawer problem. And this just had to do with speculation about the way psychological research is done. It involves what's called significance testing. And the way that works, people were already worried at the beginning of the prevalence of that method that it would lead to too many positive results. So Greenwald in 1975 conjectured that what would happen is if this methodology became adopted universally, there'd be a bias against the null hypothesis. He says, there may be relatively few publications on problems for which the null hypothesis is true. And of these, a high proportion will erroneously reject the null hypothesis. Okay, so when you reject the null hypothesis, that just means you found something significant or positive. Okay, and if you don't reject the null hypothesis, it just means it wasn't a positive or significant result. In '79, Rosenthal described a worst case scenario of this. He says, for any given research area, one cannot tell how many studies have been conducted and never reported. The extreme view of the file drawer problem is that journals are filled with the 5% of studies that show type 1 errors, false positive, while the file drawers are filled with the 95% of the studies that show non-significant results. Now, okay, that's the worst case. That's a nightmare scenario. That didn't happen, but if you look at the numbers, it's not that far off. Maybe it's not 95%, maybe it's 70%. Maybe it's 70-30. Okay, so it's not the worst, the nightmare scenario, but it's bad. Okay. And publication, so these guys were right. It turned out something like this did happen. And it was publication bias together with citation bias, and also a couple of other things like spin and outcome reporting bias. Those can interact in ways that really tend to filter out all the negative results that exist, and you end up with just basically all positive results in the literature that people read. So here's a great example of this. A bunch of researchers looked at 100 trials involving antidepressant drugs. And they actually studied carefully what happened to these 100 studies. They started out and then they followed them historically through the years to see how much they were cited, you know, what their prevalence was in people's, how many people read them and so on. And so they actually started with basically 50-50, half negative, half positive studies. The green is positive, the red is negative. And then they were able to diagnose that what happened was publication bias was the first thing that hit, and that already skewed things towards positive results, because who wants to read negative results? They're boring. This is boring. And then outcome reporting bias, only reporting certain things you found and leaving other things out. Generally because you want positive results, because they're more interesting. Now we have even fewer positive studies left. Then spin kicks in, and finally citation bias. And what you end up with in this historical case is the size of the circles is how many citations they get. So what you end up with is overwhelmingly citations to positive studies. A few negative ones are there, but they get almost no citation. No one reads them. So even though they're there, they're just not read. And so this is a really vivid example of the kind of thing that those guys in the 70s were worried about. It happened. I mean, this is almost as bad in the end. When you take into account number of citations, it's almost as bad as the 9%. This is a real thing. Now, how much this exact pattern is replicated, I don't know, but it definitely is a thing that is important. It happens. So this involves the interaction of publication bias, outcome reporting bias, spin, and citation bias. And when we put all those together, in this case, it's pretty stark historical trajectory. Okay, so outcome reporting bias, let me say more about what that is. And it's also called p-hacking. There's a lot of names for this. But basically, it's reporting things in a way that makes it unsurprising that you would have found a positive result. So here's some examples. Conducting analyses midway through your experiments to decide whether you should continue collecting data. Recording many response variables and deciding which ones to report after the analyses have been done. Deciding whether to include or drop outliers after the analysis has been done. Excluding, combining, or splitting treatment groups after the analysis has been done. And then at the end here, stopping your exploration of data once you found something significant. And that also relates back to Harkin, which we'll talk about. So the list goes on. There's a lot of selective outcome reporting things that happen. And these definitely contribute to the prevalence of positive results. Okay, I'm going to skip this. That's the technical part. Harking. Okay, so harking directly relates to this. Looking at a bunch of data until you find something significant. When you do, which is inevitable if you have enough data, then you write a paper around it as if, hey, I was always interested in this question, and I always suspected maybe this was the cause. And look, I found it. I did it. Okay. If you do this in secret, if you do this in a non-transparent way, then it's very questionable. I mean, if you're up front and you say, look, I did a bunch of exploratory analysis, I found some stuff, and here's what I found, that's fine. But if you present it as if it's actually the result of an experiment that you were already interested in performing, this is not good. This is not a thing you should do. But I just want to emphasize, there's nothing wrong with exploratory analyses, but they shouldn't be presented as if they're experimental studies. That's misleading and it's not a good thing to do. And again, contributes to the skewing to positive results. Okay, now things get very depressing because I'm going to go through a bunch of survey data of actual scientists and what they self-report in terms of their own practices. This is the scientists talking now. Okay, so here's 500 United States psychologists in 2012 surveyed, self-reported. In a paper, how many people fail to report all the study's dependent measures? 63% self-reported, they don't always do. Deciding whether to collect more data after looking to see whether the results are significant or positive. 56% of people self-report that they do this. It's just the thing we do. And not only that, the community thinks it's acceptable. It's just one of the things we do. There's nothing wrong with it. No one was ashamed of this. This was said with pride. This is how our community performs research. What's another one? Selectively reporting studies that worked. Okay, 46% of scientists say that they do that. That's just a matter of course. Okay. So this is just pretty solid evidence that these questionable practices are actually happening. This is self-reported. Now, little good news, only 0.6% of people say they falsified data. I guess that's good, but you wouldn't necessarily expect people to cop to that, in a survey. Although, when we get to the Dutch, we'll see they did actually cop to it. So things get worse, actually. Oh, you might wonder, this is the American scientists, American psychologists. Are the Italian psychologists any better? Let's see. Same study, same questions, but now here are the Italian respondents. I mean, they're a little better, maybe, on some things, but it's actually very comparable percentages. This was a study performed also by someone here in Padua, in behavioral sciences. So pretty similar result on the same questionnaire. So community standards and practice don't seem to be that different between Italian and American psychologists with respect to these practices that skew towards positive results being reported. Okay, is it just psychology? No. Here's 800 Australian ecologists and evolution theorists not too long ago. Unreported variables, well over 50% of people don't report all the variables. How many people do the harking? Well, half of people do the harking and they're fine with it. They're not ashamed. That's just what we do. Unreported models, half the people. Switching analysis in midstream, half the people. Okay, you get the idea. Okay, this is a real problem. It's a real thing. Okay, here's the gold standard. The Dutch surveyed 7,000 academic researchers a few years ago. 7,000 across all disciplines. 10% of life sciences people admitted to fabricating data in a survey. This is self-reported. That's not good. That's not good. 55% have some questionable research practice that they are happy to admit that they do. And that's pretty consistent across life sciences, social sciences, natural sciences, arts and humanities. Not that different in terms of having some questionable research practices that they're happy to tell the experimenters that they do. And again, they're not ashamed. That's just what the community does. That's how it's done. Yeah, so fabrication, it's like 10% in the life sciences. It's a little less than the other ones. Those are not good numbers. These are self-reports. I know the Dutch are honest, but this is ridiculous. I mean, 10% of scientists saying, yeah, we just make stuff up. Making stuff up is not science. I mean, we can agree that's fake science, right? That's uncontroversial. Okay. So there's definitely a problem. Okay, so, and we know what the proximal cause of some of them are. I think fraud is there. Maybe it's 10%, maybe it's less, 5 to 10%. Okay. But I think we can say with confidence, publication bias definitely is one of the proximal causes. Questionable research practices of the kinds we just saw in the survey, those are definitely happening. So those are plausible proximal causes of the crisis. Okay, but now you might wonder, oh, okay, but what are the ultimate explanations? Why did this happen? Why do these communities engage in these questionable research practices in the first place? And why do the journals why are these publication biases in favor of positive result? This question we know less about. There's a few studies that have been done, and there's conjectures that seem plausible, but I think less is known about this. But I'm just going to mention a few things that people have cited that seem like they might be probable ultimate causes. Perverse incentives, specifically incentives for productivity. Publish or perish. You've probably heard that expression. I know in the United States that's a real thing. Eminence, influence. Who doesn't want to be eminent and influential, I guess, in science? I'm a philosopher, so none of this means anything to me. No philosopher is going to be eminent. Well, maybe Socrates. And it didn't end well for him. So anyway. So why might the incentive structure, why might that be applied? Again, there's some evidence it's true, but I don't say strong, but why might it be plausible that the incentive structure is explained? Well, if you think about it, you gotta publish, and science moves fast, competitive. You want to get tenure, you want to, have good reputation, all that, that's important. And if you think about these things where you have your data and you're just selectively reporting, if that's an easy way to get a positive result, right? You don't need a fancy laboratory, you don't need a lot of resources to just be selective in what you report. So that track intuitively. These incentives seem to encourage simpler media-friendly narratives that can be sold, that you can sell and so on. It incentivizes bold, surprising, and attention-grabbing hypotheses, because who doesn't love that? Who doesn't want to read something interesting, surprising, attention-grabbing? We all do when we read stuff. And here I cite an interesting study by Sinan Aral, who's a researcher at MIT. This isn't directly related to publication, but I think it reveals something about human nature that's kind of important. They studied all the Twitter data for many years, and what they discovered was false information spreads faster than true information. And they have a plausible causal explanation based on they have a huge amount of data. And what they discovered was two things matter for the spread of information. And false things tend to have these properties. They're surprising and they're exciting. They push your buttons, right? Okay, they're attention grabbing. Those two things we know are contributing to things being viral on the web. Now, the journals aren't the web, but there's still people reading stuff. So how different really is it? I don't think it's that different. So anyway, I think there's some fundamental things about the spread of information and what kind of information we want to see in the modern world that's relevant here. And all of this would seem to lead to fewer negative results. That's intuitive. At least that's an intuitive explanation. Here's one that I think definitely is relevant. The structure of peer review. So in the way peer review works is you find your thing, you do your analysis, right? You come up with your positive result, you write a fancy story around it, and that's when the referees see it for the first time. That's kind of too late in the process. The damage is already done. All the biases are already in there. And so the Open Science Coalition that's really trying to change things in science, one of their proposed remedies is to move the peer review way up in the process and have scientists submit the question they're interested in and the experimental designs they have in mind to test that question and to do the peer review at that stage before any results are published. This, I think, is a great idea. Some journals are taking it up. I think this definitely would be very helpful, not just because, it's before all the biases kick in the analysis, but also referees tend to be protective of their own turf. So if you report some significant result that contradicts what Mr. Famous psychologist thinks, and he happens to referee your paper, or she, there tends to be a little bit of turf warfare that might happen at that later stage. But if they're refereeing early, before the results are known, there can't be any turf war. They don't know what the results are going to be. And so if the journal agrees to publish based on the quality of the question and the design before anything's known about the results, not only is that going to help with the biases and stuff, it's going to help with turf warfare amongst referees and people submitting papers, because what are you going to fight about? You don't know what's going to happen. Maybe it'll support your view. And after all, if you're still confident in yourself, why not approve the study? And finally, journal editorial practices above and beyond peer review. In a big survey of scientists, when they were asked, what do you think the distal causes of all this are? They said things like, there should be encouragement by journals to publish negative results. And also they said, the editors should get this idea out of their minds that findings should be unexpected or exciting or, attention valued. And that seems to make a lot of sense. So anyway, that's a little quick tour through what the reasons we think there's a crisis are and what some of the explanations might be for that. And I think I'll stop there. Thank you very much for your attention.
So thanks for this stimulating interesting talk. I think that was time for discussion for question and answer. Is there any question?
We've been talking about this non-stop for the past 36 hours, so I can take it.
Well, the problem for my medicine is that traditionally almost only point null hypothesis of the question. And if you have enough data that is rejected, even if it is almost equal to zero. Or further, the feedbacking is applied in the wrong methodologies. But if you have, for instance, if you have a distribution outside the regular exponential family, then the sufficient, the minimum sufficient is the full data set. In that case, you need at least n statistics in order to collect all the information provided by the data. And this
Thank you so much for those very great observations. That's absolutely true. I didn't get into the statistical methodology side of the causes, which for the students I did, and I had a whole section on what we might do to remedy that. And exactly the phenomenon we're talking about is a very important thing. I kind of left that out of this, but that's a very important thing. Statistical causes based on the statistical methodology we're using in nature of the study. Absolutely. Apologize for omitting that. Thank you for bringing that up.
I want to elaborate a little bit on the proposal for moving the review process at the design stage. I come from the world of cancer biology, and in that space, leaking to others what your lab is in the middle of doing is dangerous. And so it would be essential to implement this, they have a high level of confidentiality, but also you will be very delicate to choose reviewers for your experimental design. I mean, a little bit of this is already going on with user grants, and it's causing quite a bit of problems. So I wonder what you think about a strategy where the review process is professionalized, as it is in some disciplines, right? Where we don't rely on volunteer, where we easily stay away from the main competitors, and where we compensate reviewers for doing their job orally, potentially even going through some of the reproducibility steps, at least for very important studies. Any thoughts about this?
Thank you so much. Absolutely. Amen to all of that. That's, these are exactly the kinds of questions that will need to be asked if anything like any interventions are actually going to work, that we're actually going to get changes to be made. These are exactly the kinds of questions that we have to raise. I think it's a great idea to compensate and have a professionalization. I can, you know, I'm not a scientist, but in philosophy, it's entirely volunteer work. It's so much work to referee papers, and everyone's super busy and under pressure to do their own things. And I mean, one of my students was telling me that he's a big shot professor now. He told me that one year he refereed a paper a week for the entire year. That's the volume. That's what would be neat. I mean, for nothing. He got an award. He got a service award from one of the journals, but referee of the year. Got a plaque. You're definitely onto something very important.
Just related to this, I think that professional review is a good thing, but another thing that would improve science, I think, is open review more. So to have all the staff open, what do you think, Mark?
Oh, yeah. Yes, absolutely. And in the remedies section that I talk about with students, transparency is such an important thing, because if you just say everything you did, right, just in some form, get everything you did out there somewhere, maybe not in the journals, but in some place receptacle where everyone can see it. Yes, there's nothing like a little sunlight, if you know what I mean, like today.
So much. Good evening, everybody. Thank you so much. I came from Mars, so with a lot of language here. Thank you. But one thing that's maybe you didn't know that you didn't mention is registration, because we have background on science framework that we use it. But well, I believe in that one is also just not very friendly reaction. But some people they do that. But what if we improve that? We change to that. We have a video about registration. Thank you.
Absolutely. So I have the privilege of talking to Brian Nosek via Zoom. He gave me like an hour and a half of this time last month. And he explained to me all about pre-registration and the proposed reforms to peer review. What that open science collaboration is doing is amazing. And absolutely pre-registration of studies would be super duper helpful in conjunction with these reforms to refereeing and so on. I think we go a long way to ameliorating the problem, for sure. Absolutely.
Anybody for maths? No. I just curiosity about possible other distal cause that you didn't mention, but maybe there is also a lack of education. If people does not think that this is bad, because if they think that this is bad, they say, no, I don't specify. But if they think that maybe this is like the education, and in some sense, this is our fault. I mean, we can do something for it.
Yes, absolutely. Education also about the statistical methods that are used and their pitfalls and their problems, as was raised earlier. For sure, education, absolutely. And that falls on us. I mean, we're the teachers. And one of the great things about this summer school is we're getting them young. And they're working together and they're coming to an understanding of what this problem is. If this problem is going to be solved, it's going to require a huge amount of collaborative work across many disciplines. And that's how I start with the young science. So it's going to be 100%. That's why the summer school is so great.
Right, yeah. Any other questions from Mars, Moon? Okay, yeah.
So as I was saying, we've been talking separately about these topics a lot, but I still have not quite developed a sense for what is your perspective about the most important open problem in replicability from a philosophy of science standpoint. Do we lack conceptual tools? Do we need to advance perspectives, theories, philosophically, to be able to make progress in this and understand this phenomenon and approach it at a better way?
I sure hope so, because that would make me somewhat relevant to the practice of science. So, boy, I hope that would be helpful. Yes, and I should say there are some. It's only recently philosophers of science have really gotten into this. And I should mention a few people: Edouard Mascherini at the University of Pittsburgh, Jan Sprenger, who's here at the University of Turin, and Felipe Romero, who's in Groningen. These guys are really doing some amazing work on their students and their groups to really have a conceptual framework for understanding what the problem is and what kinds of interventions might be helpful. So I'm hoping, because I want to be helpful to the problem. So I really do think there's an important place for philosophy of science at a conceptual level to just give us the concepts that we can use to really clearly think about the problem, what it is, and what changes might help. So I hope that's true. Looking at the work of these people that are doing work now, I'm very optimistic that it will be helpful. And the young students of the philosophy and stats, they're the ones that are going to solve this.
Thanks. Any other questions? Okay.
Thank you
very
so much.
Okay. The next talk,
I think this is you, man. I think is that you? I think so.
So the next talk is by Professor Giovanni Parmigiani from Harvard University. Title is Replicability and decision theory. Thanks again. Also for the lecture.
Tough act to follow, my friend. I think you nailed everything. You started by nailing the thank you to the organizers and the reason why this has been such a great place. And I want to join you in that vote. Thanks, particularly to the organizers of the workshop, but also all the students who gave us quite a bit to think about. We continue to do so all the way to the end of the week. So it's been remarkable so far, and I'm really looking forward to the rest of the week. I'll be around for the rest of the week, incessantly talking about replicability, and up until jumping back on my flight to Boston over the weekend, and so be happy to chat. We're hanging out in the courtyard in the Department of Statistics, drinking coffee and watching the students learn, because most of our lecturing job is done, but I think our real job's not seen. But for this thought, it says number 3 before the title, because it was the third of 3 elements that I had prepared. The way we organize it is that Brandon took care of the general scheme, and I was getting at it from the very opposite end, taking a very specific case study in the application of machine learning to ovarian cancer prognostication, and looking at real collections of studies that put them together and up and bring it. to relevance in this particular space, and we slowly but steadily got closer and closer on that. And I was hoping to, stage one was the case study. Stage two was looking at the National Academy of Sciences report, and stage three was my attempt of moving beyond that and maybe giving a proposal for thinking about replicability in the space of prediction. So I hope that the fact that we're jumping in on the third floor here will not be too much of a compounder. If you'd like to interrupt me and ask me to slow down and elaborate on anything, please feel free. But with the students, we spent quite a bit of time thinking about a National Academy of Sciences report called Reproducibility and Replicability in Science. It came out in 2019 in response to sort of general concerns about the so-called replicability crisis and some of the evidence for that. That was the mandate of the committee. It's easy to find. The PDF is available from the website of the National Academy. If you are interested in this topic, it is really highly recommended reading. It's very thoughtful, and it's balanced, and it has the abundance of really interesting references, which is then, if you got the QR of his file and his 100 and some references, you also get everything that happened between 2019 and 2023, including the Mascherli and Romeo and stuff. So between these two references, you can get caught up on this topic very, very reliably. How do they define replicability? They define replicability as obtaining consistent results across studies that are aimed at answering the same scientific question, each of which has gathered its own data. And we spent quite a bit of time with the students noticing that this is really turning one definition into four. You have to know what you mean by consistent, you have to know what you mean by study, you have to know what you mean by answering, not a small thing, and you have to figure out what the data is and how it's defined and who decides what data is relevant for what. And so we'll retrace a little bit of this journey in my presentation as well, but in the context of trying to develop a parallel definition and maybe a little bit of a theory to go with that about prediction. If you go to the National Academy report and do the simplest NLP analysis of all times and do a search for hypothesis, it comes up 23 times, the word hypothesis. The word prediction comes up 3 times, and it's always in some gray area that doesn't really have very much to do with what we think about prediction. But I think the replicability of prediction algorithm is a very important aspect of how we think about the scientific enterprise in general, in my view. I feel it in my work every day, because I work in a cancer center and I'm very interested in giving patients a reliable risk assessment about how the genes they inherited puts them at risk of cancer, about whether certain drugs will facilitate their recovery from cancer, just about any step of the long journey to this terrible disease, including one before it happens, has some element that can be supported by various aspects of prediction and machine learning. And the main bottleneck in translating what we can do as statisticians, bioinformaticians, computational biologists in that space, and getting to the patient is the ability to demonstrate that what you're doing is generalizable enough. So replicability, translatability, so to speak, of these algorithms to different contexts and approaches is really a fundamental part of translation of the basic science work that we do into the clinic. So that's why I'm interested. That's the perspective that I bring to this. Maybe some of my theories are too heavily influenced by it, but I hope that I will also bring something generalizable beyond this field specifically. And I come from sort of a very sort of predictivist upbringing in terms of my statistical training back back in the day of working with or under the guidance of Ciparelli and so forth when I was a student. So this all adds up to me as something that's worth thinking about. There are also a couple of aspects of the National Academy's report that points, to me at least, from my vantage point, towards the decision theory in a very clear way. One of the things they notice, for example, is that the extent of non-replicability across science requires different and multiple criteria for determining a successful replication in different fields. So how do we determine these criteria? To me, one simple way to think about it is to figure out what questions you're trying to answer, what decisions you're trying to make using either the conclusions or the predictions, and go from there in developing the criteria. That's the perspective. The other complaint or comment they make is that there is no standard across science for assessing replication between two studies. Is this good or bad? I don't think it's all that bad. I think if we were to try to find a sort of one-size-fits-all definition of replication, we'd probably have people do things that are a misfit for the real need of their field. And I think the way to conjugate the question about replication with the needs of that field can be, at least in some circumstances, a decision to replicate. So that's, and I think I've showed you this picture 17 times, so maybe it's time to stop and go to something slightly different. Most of my experience in this space comes from cancer research, as I was saying, but I will try to have a fil rouge throughout the talk that is a different application, in part because I want to be a little bit neutral to it. And so I've taken this study, which is a study published in Diabetes Research and made by investigators with whom I don't have any acquaintance or relationship. They're interested in algorithms that take images of the retina taken as part of regular follow-up visits of patients and try to understand whether these patients have a condition called retinopathy. And I don't know very much about cancer, but I know absolutely zero about ophthalmology. So please take this in the abstract and use this example just to have a concrete idea of what I'm talking. So there are algorithms where you feed in a picture that is taken as part of the visit, and out pops a score that tells them the probability of retinopathy or a classification as someone having a likely retinopathy. This classification is subsequently used for making a follow-up visit that is more accurate. And so there is a clear decision. There's a triaging of people whose picture is suspicious based on the prediction algorithm are then brought forth for a more accurate eye examination. So it's good. It's not a very scary problem. It's not something we can talk about without thinking about very sad things. But it is a concrete application of what I'm thinking about. This study is a study where they looked at the veteran administration system, which I will inevitably end up calling the VA. So I'll just tell you that that's the term I'm going to use for it, where they have a pretty formidable IT infrastructure for a standardized data system across the whole set of hospitals around the United States. These are hospitals that support veterans, and sadly enough, we've been in enough wars that we have a ton of veterans around in the United States. They looked at two different places in the VA system. One is near Seattle. It's a Puget Sound VA something, and the other one is in Atlanta. The part of the question that is asked is, are the algorithms that are available for doing this task of comparable accuracy for the clinical task? But part of the question they're going to ask is, are these algorithms going to be robust across these various VA locations? So it's a miniature version of the problem that I want to approach more generally. I'll say a little bit more on this. So the way I'm going to think about decision theory is not the standard statistical single agent decision theory that we all, or some of us know and love, and I grew up with. That comes from, say, Ramsey Savage, Lindley, that type of lineage. It is some weird hybrid of multi-agent decision theory, game theory, and I'm not really sure. And the reason I don't know how to fit it into any of these frameworks is that in this case, there are many players in the game. There are 5 companies who provide these machine learning algorithms or prediction algorithms. There's a total of 7 algorithms in the study, 5 different companies. And that's a subset actually of the number of companies they initially contacted. This is a bit of a biased subset because it is the company who were willing to have their algorithms evaluated within a study like this. But we'll set that aside. This is a criticism potentially or a potential limitation of the study, but not of the overall concept. We can, for the purpose of this discussion, pretend that that's the entire list. So there are the companies on one side. Companies win if their algorithms get adopted in the VA. Probably they get major licensing fees and so forth. And plus they can go around and say the VA uses this, and then they can sell it to Epic and all that sort of stuff. So the company that is a clear set of interest in the success of the approaches. Of course, they have a vested interest in replicability, but their main driver is financial. Then the users of these approaches are a whole bunch of doctors in the VA system. There are many users in this case. They each have the problem of deciding when to send the patient to the follow-up visit. So first of all, there's many doctors. We can think about them in the abstract as the VA doctor, maybe, maybe not. Maybe some of these doctors are consultants for some of these companies, so maybe we have to be careful about that. Do the doctors care about the replicability? It's certainly a good thing, but their utility function, so to speak, may be different. They, probably well aligned with the well-being of the patient and striking a reasonable balance between sensitivity and specificity of the operation of this algorithm. Then there's the VA system as a whole. And one way in which the doctors might be ranked is whether the application of this algorithm in the VA system is sufficient to make the clinic that they operate break even from a budgetary standpoint. Maybe they can only do enough, as many follow-up visits as they have budget to do. And that's actually how they conceptualize the utility function that they use there. They have an explicit utility function, which is why I picked them as my poster children of this idea. And then there's this guy, Yanagihara, Blazes, Young, Chi, Gencarella. These are part of the game as well. They are the folks who have decided that they're going to do Seattle and Atlanta and maybe not the VA in Boston, and why. They are the folks who are going to run the analysis. They are the brokers of the integrity of the data. They do the study. They are assessing these algorithms, and in particular, their replicability. Okay. So my scheme will have these, and I'm going to jump. If I had my glasses on, I could jump to the right place. Give me a second. Because I went a little bit out of order from what I was planning initially. Way out of order. Yeah, so here I am. For the retinopathy example, there are modelers, and I'm going to use that term throughout. These are the industry provider of the AI algorithm. There are users, Those are the physicians in the VA. And there are assessors, in this case, Lee et al. Okay. In more abstract, the model is whoever generates predictions, and I'm going to call a scoring rule or a prediction rule with phi, some function of the data. I'll give you more formal definitions in a second. Unfortunately, I'm going in reverse right now. There's an agent. The agent is the individual in this scheme who is using the prediction rule for solving some practical problem in the real world. Okay? And then there are the assessors. So I want to go towards the definition of replicability, where in the eye of the assessor, the modeler's tool, in the specific context of the user's decision problem that we are thinking about, is providing a similar average utility across different studies. It's a mouthful, and we'll unpack this step by step. But that's the paper essentially, plus some notation and a bunch of apologies, because it's difficult to do this without making major simplifications all over the places. But I'll tell you where to read about the apologies and march on for the purpose of the presentation. Let me stop here and see if people have questions, because I want everybody to be on, not maybe on the same page, to maybe disagree with me, but at least understand where I'm headed. All right, good. I have to say that your students are a lot more fun in fact that these guys brought in the supplement. But anyway, we'll leave that. We'll leave that for a later discussion. So, yeah, this is the retinopathy. I told you all about this. Where is my yeah. Yes. Okay. So let's go into here. So for the purpose of our discussion, a prediction is going to be some sort of statement called P that belongs to some space P that we make about a future or unknown observable Y. In machine learning, Y would be the label. In statistics, the outcome. It can be binary, it can be continuous, whatever you want. P can be an entire probability distribution on future events. It can be even a probability distribution on a probability distribution. Or in the simplest case, it can be just a 0-1 call, as it may be in the VA exam. So it can be 0-1 call, it can be some numeric score, it can be a probability distribution or something even more complicated than that. I'm leaving that as a general. A prediction rule, which is what's really being evaluated here, is some recipe for going from an observation X about some features about individuals in a population to a point in P. So it's a mapping from the space of features, if you want, to the space of prediction. And I'm going to use two P's in this talk. The P that you see there is a prediction rule that gives you a general point in P. But when I talk about binary rules, I will use the script, the one that comes out as the way you write in handwriting. Okay. So yeah. So that's the definition of a prediction and prediction rule, and we use this notation. So in this notation, I can encapsulate what I was describing earlier as my way of thinking about replicability in this concept in this revised version of the National Academy definition. So the definition now would read as replicability is obtaining consistent results across studies suitable to address the same scientific prediction question, each of which has obtained its own data. This is the same as the National Academy definition, except for the word prediction, which I spliced in. It didn't exist before. I want to make it specific to this context. And for the fact that I replaced the word suitable for studies that have been designed for the deliberate purpose of. And I'm going to elaborate on this. So the NIS report, the original wording, it had in it the that replication is the act of repeating an entire study independent of the original investigator without the use of the original data. So it asks a question that is specific for a study. To define replication, you need to have a study in the first place. And then you ask the question of how this can be replicated. And the replication data is data that is collected deliberately from that for that purpose. I'm going to call this replication by design. It is super interesting. And of course, if replication of that study is what you're interested in, it is a very powerful way to go. But in the application of machine learning in health, at least, and I think in many other fields of science, I think we need to understand the replicability, not just about one specific algorithm in one specific study, but of classes of algorithms, or maybe tasks defined more generically, as in, can we predict whether someone will get melanoma based on sleep data? So I want a theory that helps me in that type of task as well. It's more vaguely defined, but it is important. And the way I like to think about that is that for that type of situation, we can still have the assessor define a relevant collection of studies that is pertinent to asking the replicability question for the task at hand. And I'm going to call that observational replicability for very obvious reasons. It's not a designed experiment or with replicability in mind. It is maybe a comprehensive review of all data available, or something the assessor considers sufficiently systematic and not haphazard or capricious to evaluate replicability. Okay, questions? So this gets us a little bit closer at being able to home in on this notion of a collection of study, which is germane to this whole enterprise. Notation for that is big S, curly S. I think that Beamer killed my curly S. It used to be very, very curly with a long. It's now looks like a regular capital S. But big S is a collection of studies. Each unit in one study is a point in X times Y, so we have the covariates and the labels. And then a study of size n is a point in that space, X times Y to the n, and the sample size of each study is n sub k, where k is the study index. So nothing particularly profound here, just a little bit of definition. But the assessors are the ones who are in charge of determining what constitutes a study, whether a study is included or not in this collection, what constitutes a valid way of measuring each of those covariates, what's the integrity of the evaluation of the labels based on which we are going to do the ground truth evaluation. These are all problems that are far, in many applications, far from being objectively determined. And I think they're best understood from a standpoint of some sort of intersubjective agreement of individuals who have some notion of what data we're talking about and nothing at stake in the replicability of these algorithms in an ideal world. And this is where because the assessors might be very happy if these algorithms are replicable, right? And they may have a vested interest or sort of a genuine scientific interest in having found replicable ways of telling whether or not there's retinopathy based on a simple photograph. It's a good thing to do. But at the same time, we don't want them to have the same incentives as the modelers who are going to make money or not, depending on whether that is true. So this is not an adversarial situation. The assessor would be very happy to say, yeah, this works like a charm, but they don't make any money. We want to make sure that they don't make any money. So it's not adversarial, but it's not completely aligned in terms of the utilities either. So I haven't figured out a way of cramming it into either single agent decision theory or game theory, but I will someday, hopefully. back. This, by the way, is I wrote this paper at the tail end of our symposium last year for the 800th anniversary. So I'm particularly grateful to everybody who offered thoughts on this, and maybe this would be an incentive for me to nail the game theoretic version of it someday. Okay. Yeah, so in the retinopathy example, that's the cohort, the assessors define what the study is, R, K is equal to, and we're interested in a bunch of things, including whether or not the discrimination is comparable in the two main VA locations. This I've already told you, this is. So to proceed here, what did I forget? What did I forget to tell you? I forgot to comment on that 1, 2, or 3. The 1, 2, or 3 is there to remind me to alert you to the fact that these 3 roles don't necessarily need to be held by separate entities. And very often it's the same entity that wears all 3 hats. More plausible is a situation where the modeler is also the agent, but there's an external assessor. Let me give you an example of that. Banks use machine learning approaches to classify candidates for loans based on a bunch of covariates that they collect at some initial interview. They develop these algorithms. They don't want to tell anybody what the algorithms are, in fact, very often, and they apply them. So the utility of the modeler and the agent are very tightly linked. But there's a strong push to evaluate these algorithms externally for a bunch of issues that are very closely allied to replicability. For example, the extent to which they can be applied abroad, or the extent to which, if you think about the study as a particular protected group, blacks, gays, whatever you want, whether there's replicability of the performance across those groups, or are you differentially giving access to credit to different groups depending on biases that are built in, consciously or not, in your algorithm? That's just an example where the modeler and the agent are one and the same, and where the replicability can be sort of slightly recast in terms of is this replicable across different substrate of society that are of interest.
Maybe I'm confusing something, but I think that in this case you present, you have a kind of three-dimensional problem of replicability. So because you have different study, and I think that in each study a different algorithm is used. So and you are trying to check or assess the replicability of prediction. So could be an idea to try to see how an algorithm perform across studies and do this for all the algorithms, or is not a problem? I don't get it.
No, thank you for reminding me of this. I should have clarified that just like in the VA example, you have these companies who have developed these algorithms and now they froze them, they got them FDA approved, and they sell them to hospitals. So that is set. And then you evaluate them on a collection of studies. This is something I should have clarified more forcefully, because it's very different from a situation that you've heard me talk about 20 million times, where we do cross-study validation or every possible pairwise combination of training and validation on collections of study, or the sort of stuff that I always babble about. No, thank you. That was super helpful. So the formalism for the modeler agent is that my keys are kind of just fading in the background, but here lives the key. And it's the scoring rule, the frozen scoring rule that we're evaluating. The modeler also has some probability distribution or probability model on X and Y. And then X and Y as they apply to, in this case, the next patient coming to the VA. And then they have a utility function.
a utility that depends on the action they're choosing from in some space curly A, and the true label of the person they're about to classify. That utility function has a comma between the A and the Y, and the little part of the comma that is kind of fading in the background as well. So this is a standard notation. There's nothing weird there. I mean, it looks like something. Okay, a couple of comments here that make this this replicability space a little unique. The predictions are applied to individuals. The decisions are made one patient at a time. Do you go to the follow-up or not? This is different from what Brendan was talking about, where the conclusions about replicability are about something a little bit more abstract and fluid, perhaps, which is maybe a property of a study, or maybe a property of a universe, or maybe property of a population, if you are in the sort of standard statistics 101 fairy tale. This is one person at a time. The second difference that's even bigger is that I know why. Now I'm the assessor. Now I'm looking back at what the VA did in the past X years. I think it was 2005, 2023 or something like that. And I know what happened to that patient. So I have the labels. So both of these are giving me tools to do something a little bit more forceful than it's normally possible. Then, from the standpoint of the user is a rational utility maximizer Bayesian. In this case, they have their prior on the future patients. They are using this algorithm purely as a tool. They cannot even open the black box. They get T, and their question is based on, I have some function of my data X based on some function. How can I optimally decide whether to send the patient to the follow-up or not? Okay. So the assumption is that in one version of this story, the agent is a fully Bayesian agent. This version of pretending, while the assessor is a little bit more sort of a standoffish type. It's more like an exploratory analysis from the assessor's standpoint. The developer can be anything. The developer can be a Bayesian. They can do whatever they want. They are only interested in the prediction performance of what they do, and I like to think of them as you know, an algorithmic type in the dichotomy that Bryman makes between algorithmic and inferential breeds and statisticians. So in the 3-character version, you have all 3 species of statisticians: the exploratory descriptive, the Bayesian decision maker, and the algorithmic Bryman using one. Okay, one way to think about it. Okay, but the agent now has solved this problem. They have the delta star. The delta star is a recipe for taking the score that comes out of the machine and deciding whether the patient goes forward to the follow-up exam or not. So based on this, I can apply delta star to the utility. Now I'm the assessor. The user has been kind enough to tell them their utility function. And what I can do is I can take delta star, apply it to all my retrospective data, every pair of X and Y, evaluate the observed utility function for every point in the VA study from back in 2005 to now, calculate that utility, and maybe take some summary. The concept here is that the interesting part here is the distribution of those U's in the collection of studies. And one definition is based on averaging those within study and comparing them across study. But here, really, there's a million ways to summarize this depending on how you want to approach this problem. One definition is to calculate a study-specific average of the utilities, which you see at the bottom, and then define a study to be replicable. This gives you already a quantitative version of replicability, one that is rather nuanced. You can look at now a matrix, K by K matrix, with every pairwise comparisons, and understand every possible pairwise replicability gap between these various studies and populations, and in a quantitative way that is on a scale that is relevant to the user decision making. So, when I was writing this, I was very tempted to stop here. But for reasons that still are not unclear to me either, I decided to give a definition. And so one possible very strict definition, if I want to say that something by golly is definitely replicable, what I would do, I would take the max of that matrix, look at the largest deviation and say, I want that deviation to be small. And so I bound it by some epsilon and define that to be epsilon replicability. But that, I could do it 10 different ways. I could do it relatively, for example, as opposed to absolute utility. That's less of a relevant part. The important thing is to focus on that distribution as a descriptor of the replicability of the prediction. So that's that, because my paper was about defining replicability, and I have in the discussion I have a bunch of examples and special cases. So practically, this is it. So how are we doing with time?
Okay.
All right, so maybe another 10-15 for elaborating us on a couple of things. So one thing that I find interesting and haven't quite thought through, but maybe you guys can help me, is this issue of dominance. This is a situation where I'm looking at two studies, and I have my curly U. Remember, the curly U is the average utility for the user within that study. And I'm looking at U1 and U2 in the two studies. And I have three algorithms there, algorithm A, B, and C. And let's say that my band along the diagonal is of size X. So the diagonal line is epsilon away. The dashed line are epsilon away from the diagonal, the one that go up and down. So A and B are both replicable by that definition. And I can also go back to the users and the VA system and say, look, A and B are both replicable, but B is performing quite a bit better in terms of utility. Piece of cake. There's dominance there from this standpoint, in this hypothetical multi-criterion way of thinking. If I look at C, however, there's a trade-off there, because if, for example, if I was to choose between C and A, I would have to trade off replicability for performance, at least for performance in one of the two settings. And so there's no solution to this. This is really a problem where there are different objectives. And the high level of utility in a future study is often the objective of the validation of a clinical prediction algorithm. And you want the utility to be high and sufficient for the task at hand from a clinical standpoint. And that sometimes comes at the expense of replicability, when it can be learned with greater accuracy how to proceed within certain populations or with certain technologies that are not available generally, or when you can look at 10 million SNPs instead of 850 or many. So I just wanted to clarify that this is a bit of a different exercise from validation. You just look essentially at stability measurement of the performance, and the metric for the performance is embedded in the utility function of the user. A lot of the literature in this space is about validating model, and develop it here, then you get a new study. Does about great question, difficult question still, but not this question. In the binary case, I'm looking. There's a lot that can be sort of developed if you are thinking about prediction rules that just give you a 0-1 answer. And for those, you can play around with a lot of the utility functions that are typically used in these cases for classification or for hypothesis testing. And one, for example, that is super simple is to get a correct proportion classified back as one of the criteria by simply setting the utility to be 1 if p is exactly equal to y and 0 otherwise. Both types of error are equally painful. It's an assumption. Just look at how many times you get the right answer. This falls out of the special. One thing doesn't fall out of the special case is ROC analysis. That is conditional on the outcome. And all of these arguments are marginal with respect to the outcome. The decision maker has to average out y in calculating the expected improvement. So there's no ignoring prevalence, and that's an important sort of corollary to this. This is not to say that RFPNI is not interesting, but it is to say that I haven't found a decision threatening justification in this context for you. Yeah. Using the same machinery, you can define replicability based on bypassing the user completely and asking the question from an assessor standpoint about differences between the different studies by going to upstream from that utility function evaluation and looking directly at the joint distribution of these points, p of x, and y, defining the empirical distribution of these triplets across the different studies and trying to figure out how different they are across. It's a purely descriptive way of understanding these differences that could be in. That's I know I bring it up to show you what is lost and what goes away. Take the user out and take the utility out. That there is at least some of this machinery that remains alive, and that can be used to explain descriptively what many of the studies that currently look at the replicability are attempting to do. Okay. Yeah, so as I was mentioning earlier, I would really like to get this also stretched out all the way to decision theory in terms of having this multi-agent, to statistical inference in terms of this multi-agent approach. And there are some examples that can provide a foundation for this. For example, drug testing in clinical trials is one where there are drug companies providing the drug, there are scientists who are running the trials, and then there are patients who are benefiting or not from the trials. But there are still some conceptual challenges that need to work on. One is that the decisions are not applied to individuals, but to studies with populations, and one is that the truth is not ultimately available as readily as it is. So with that, I'm going to open it up for questions. This is all summarized in a paper that is about pure statistical science. If you go to the statistical science future paper pages, it's listed there. So I am not as fancy as Brandon, who has the QR code. I have to ask ChatGPT how you do that. That was way cool. But I think you can handle it with Google for now. And if you're interested in the paper, it's all there. So questions. Yes.
Did you face a few for you? That's the short question. Did you face most of the problem of clustering and not that classification? I mean,
unsupervised. Yeah. Not with this machinery. Whether I face it on a daily basis, the answer is obviously yes. But whether I have solutions about the replicability of clustering. So yeah. I was hoping to make some progress in replicability of clustering. And we have a paper in statistical science last year with Lorenzo Trippa and Lorenzo Mazzolero and Svetlana Tikucheva and another student. Name I'm embarrassingly blanking on it. But what we do is a review of concepts and methods for looking at replicability of clustering across spectrums. We're not very far along as a field in thinking about that. It's a challenging problem, but at least there you see, if you're interested in that topic, you can see where the field is at and where some of the concepts are looking at. Great.
Thank you, Dan. That's great. I was wondering, maybe you could say something a little about the connection between this and more traditional ways of thinking about application and maybe more specifically, would there be a way at some abstract level to model the traditional notion of replication within this framework? Or is it really just orthogonal to the more traditional way of thinking about replication?
So. Something for us maybe to mull over for the rest of the week. Take the luxury framework, where the replication is defined very specifically with a fixed methodology for statistical analysis and a clear definition of what aspects of the experiment were the result of some random draw from the population and were fixed. Thinking about the replication experiment there and replicability in that context, and have the statistical analysis be driven by a decision theoretic question. So now the luxury experiment is not, looking at a p-value or looking at a posterior probability, is looking at solving a specific decision problem using the data. And would the replication give you similar utility if you did it again under those conditions? Something along these lines could help us tie the two concepts together.
We are very sure and they
Very one. Why do you think that there's a lot of work about replicability in terms of hypothesis testing, whereas very, very few works about prediction or machine learning? Just because they are new or
Honestly, if you are doing hypothesis testing, you're automatically going to run into a lot more replicability trouble just because you're not looking at an interesting scientific problem or a well-defined one. I hope this was not recorded, but that's what I really think. I mean, particularly point hypotheses are really an ill-posed scientific problem. Professor Pesarin pointed that out before me, so at least I have one other twin soul that thinks about single. So maybe it's easier to run into a replicability crisis if you think about hypotheses. Predictions are verifiable, right? They're a lot closer to being self-correct. But I think it still makes sense to think about the replicability, particularly if we want to think about generalizability of everything that we're learning about machine learning today. In precision medicine, it is really a key challenge. In this space, the boundary between the problem of replication and the problem of generalizability or multitask learning or domain generalization or even domain adaptation are much fuzzier than they would be in the space that Brendan was talking about. Thank you. Thank you.
So if there is no other question, we can stop here. Okay, thanks. There is another question.
Hey, no, that's great. You on the microphone?
Oh, it's very good.
Thank you very much. I want to ask if, in your opinion, this kind of mathematics can be useful to also evaluate how a specific method, algorithm, for example, can be influenced by different factors. So, for example, I performed a study of identification of something with a specific set of parameters. Then the second study is by changing some parameters and so on. So, can with this, with the result of this mathematics, also have yes, information about the influence of parameters.
I'm not completely sure about what you mean by parameters, but and I'm not taking it in the statistical terminology. I imagine maybe parameters of how you carry out the laboratory experiment, or yes, that's great. And I think the answer is yes. That's exactly the spirit. The way one would ideally collect these collections of studies is to make them similar enough that it makes sense to ask the same question, but different enough that there is variation that reflects the type of variation that you can expect when you apply it in the future. Otherwise, there's no point in being replicable, really. The reason why we want science to be replicable is that we want to reliably use it in the future.
So I can also have information about the stability of a specific algorithm.
Yes.
If I take different algorithms and I want to see how they are replicable, of course I can use this, but
Also, I can, with the same algorithm, perform different studies and see how the algorithm is stable in evaluating specific outputs.
If I understand your question right, it's a slightly different question. So if you have an algorithm as opposed to a specific prediction rule that is frozen and approved by the FDA, then you are learning each study, and you could be learning a different algorithm in each of the studies. And then you can ask the question: if I train, say, rainforest in this study, and then I retrain it here, do I get answers that are comparable? And how do I go about thinking about that? That's a great problem, but it's a slightly different problem. It's a problem that I'm very, very interested in. And a lot of what my students and I do is to think about something that we call multi-study learning, where one of the architectures that we like is one where we start from the same collection of the studies that you would use to evaluate replicability, and build algorithms that are hopefully generalizable to future similar studies, in at least in the simplest incarnation, in a two-step procedure. That is a generalization of an algorithm, beautiful algorithm by Brian with stacking. So you first develop a predictor or a set of predictors within each study, right? So let's say that let's just take the example of a random forest. Do random forest, K random forest. Then with each of these K predictors that you have, you now calculate predictions across every data point. So for each point, you now have K different predictions. For study one, the top row of this, or the predictions from the first algorithm are in sample prediction from the same random forest that you've trained on study one. But the other K-1 are the ones that you've trained on all the other studies. So now you throw away the original data, keep this now K-dimensional set of features, merge the data, and retrain. If you do that, it's a very simple idea, but you end up rewarding the algorithms that have a better ability to predict well when they're trained in one study and evaluated in another. And this gives you a way of ensembling these study-specific algorithm in a way that tends to generalize that. So if you're interested in that, I'm always happy to talk about it at great length.
thank you very much.
Any other questions? So, there is no question. Control site. Second sort of annoyed, historical building, the second point they discovered that the roof was collapsing, and so they needed some very, very important to store it immediately afterwards. We can like this place, and third, we can combine 20 to 5 so we can have time for talk. Thanks again for the speaker and see you.
Brandon, is this your flash drive? Is this your flash drive?
No, that's it, yep.
We survived.
Yeah, we can.
Perché ho sbagliato a... No, dimmi. Guarda, mi è assolutamente sul nuovo, ma guarda, lascia perdere. A livello un po' da ricevo solo niente. Trovo più me li rispedisco. Hai una chiavetta per casa, Max? Sì. Qui no. Allora, questi qua li tiriamo fuori. Questo lo chiudiamo. Analizza e correggi. No. Come si chiama il file che sono prima per me è presentazione, così. Vai per numero. Presentazione, eccolo qua, aspetta, presentazione reproduction, perché presentazione paradosso. Insomma,
sono miei chiavetti.
Presentazione paradosso. Presentazione production. Oh, eccolo qua. Tiro giù, faccio così. Come si fa a togliere? Ok. Vediamo se è compatibile. Ah, non ha l'animazione. Ah, giusto. Questo lo posso chiudere? Non lo puoi chiudere, non basta? Ah, chiudi le schede, chiudi scheda corrente. Chiudi. Questo lo passiamo solo.
Condividere lo schermo si è restato.
Che la finestra condivisa è stata chiusa. Ah, era la condivisione.
Gli chiediamo.
Sì.
No.
Sì, è tutta la presentazione. Vediamo in prospettiva.
Yeah, not Welcome again. We start with second part of the workshop, dedicated to the other university scientists or philosophers. The first one is Marcus Valley from CRISPR. She will talk to us about reproduction and interest of mass discrimination production.
Okay. Yes, thank you. Thank you for the organizer for inviting me to take this small talk. It's a work that is at the beginning, so I would like to know your impression. This is a talk that is very different from the talks we have seen before, we have heard before, and is mainly on the main problem is that when we use reproduction techniques, what kind of reasoning there is behind that, how they are justified. Okay, so that's the main problem. First of all, I'll be very, very simple. I'm sorry, but as an excuse, I can say that this is the distinction that is drawn by Nancy Cartwright in one of his articles. I will tell you about it in a few minutes. And she starts from this distinction. So replicating is doing the same experiment or study again, just running an experiment that is as much as possible similar to the original one, in order to obtain the same result. Not a lot of problems behind it, but I will skip it. It's not necessary to discuss what we are going to discuss. And reproduce, doing new experiments. What does new experiment mean? Significantly different. We will see what significantly means for Cartwright from the original one in order to obtain the same result again. Okay. So this is the work by Nancy Cartwright. It's written in this edition because I was supposed to talk also about other two works, but I ran out of time, so I will not speak about the other two works. Nancy Cartwright, the title is Replicability, Reproducibility, and Robustness, Comments on Harry Collins, and it's been published in 1991 in History of Political Economy. In fact, it's not a comment on Harry Collins. I don't know why she went this way. She just said, okay, I agree with Collins' thesis, but she argued more on a practical level. I will shift the same point on an epistemological level. Okay, that's all, the reference to Harry Collins. And here I just mentioned three main points of her arguments. Then we will see them in details. First of all, reproduction functions as a kind of inference to the best explanation. This is the first assumption. Second assumption, reproduction in economics is identified with the implementation of different models for the study of the same phenomenon. Okay, this is our starting point. The conclusion is that reproduction is not justified in economic practice. Okay, so let's see what she said. So the other two words, but are. So very, very roughly, inference to the best explanation. There are a lot of problems behind this type of reasoning. It is studied a lot, but this is just a sketch. Let's say it's just a schematic presentation. Is a non-deductive inference structured in the following way. We have a certain surprising style of data. Second, the hypothesis H provides the best explanation for D. D is the set of data. Hence, H is true. It's non-deductive, so we don't have the certainty of the truth of H, just a certain probability maybe. There are a lot of things here to be discussed. What does it mean to be an explanation? What does it mean that an explanation is better than another one? And so on. But we don't need to enter into these details to discuss Nancy Cartwright argument. And here is the slide with a sort of schema that will be completed eventually in the end of this talk. And so this is our response. H is the hypothesis that best explains the data we have. We use IB, so H is probably true. This is a starting point. She applies this way of reasoning, first of all, to a specific event, say, an important event in physics, that are the Jean-Perrent experiments. Okay. The conclusion is that there are atoms. We will see it in detail a little bit in a few minutes. The conclusion she draws is that it's not okay. This is not of interest for economics, because they are not interested in the realism anti-realism debate. So they are not interested in this kind of conclusions. So it's not good to analyze reproduction in this way. Let's see. I just tell you a few information about Jean-Perrent experiments because my idea is to see to show you what Nancy Cartwright think about the Jean-Perrent experiment. For all the 19th century until the beginning of the 20th century, there was no consensus about the existence of atoms. Okay, so part of the physicists and chemist community don't agree on that. Until a certain point, at the beginning of the 20th century, when Jean-Perrent published 13 different experiments. These experiments each aimed at determining the value of n. This is the Avogadro number. Okay, the Avogadro number is the number of atoms, molecules, or ions presented in a certain quantity of matter. Let's see. Until then, the existence of atoms and the Avogadro number as well was mainly an hypothesis. Okay, they admit this kind of hypothesis, for example, Poincaré admitted because attribute to them a role in science because they have no problem in admitting that imagination can have a role in science. So they admit. But after Perrent published his experiments and the result of these experiments, well, a lot of people changed their minds. Okay, and they start to think that atoms really exist. Why? Because the calculation of the Avogadro's number was exactly, let's say exactly the same for all the 13 experiments. So what's the point here? The point is that the 13 experiments are based on very different methodologies, very different setup of the experiment, because each experiment studies different phenomena: Brownian motion, electrolysis, alpha decay, so very different experiments. The point is that in all the equation involved in understanding the experiments was present the Avogadro's number. So I calculated the Avogadro's number and the result was the same. And so one famous expression is by Poincaré, who said, well, if we can count them, then they exist. Okay, so this strikes the community. It's a very strong result. And this is presented as a clear case of reproduction in inference to the best explanation. The big point is that, the important point is that the experiment must be independent one from the other. What does it mean for Nancy Cartwright? Is that they need to have different auxiliary hypotheses. So the background hypothesis we accept in order to understand the result of the experiments need to be different. Okay, this is the independence. And this is in literature is something that the word robustness and is discussed as robustness. We will not talk about robustness directly here. So here, the first tentative goes wrong very quickly because the conclusion of this inference to the best explanation, the type of inference to the best explanation is of realism and realism type, and economists are not interested in this type of conclusions. So Nancy Cartwright tried another strategy. So she still uses inference to the best explanation, but the hypothesis changes. Okay, so the hypothesis that makes the explanatory work, and that is supposed to be confirmed, is that the different tools is not the different strategies that we use to calculate n are all reliable strategies. That's the conclusion. It's not the conclusion that the atoms really exist. It's the conclusion about the reliability of strategies. Okay. And I call this new this proposal by Nancy Cartwright the witnesses IB analysis, because we will see it in a moment. She uses this metaphor of witnesses. Okay. This option seems to be more promising at the beginning, but in fact, it doesn't work as well. And the reason why it doesn't work is a little bit intuitive. It's not clearly stated. We will see it together. And but let's see the witnesses strategy. We may think of a situation in which we have different witnesses that give testimony on the same fact. And we may have some reason to question the reliability of each of the witnesses for different reasons. But once we satisfy these two conditions, we are sure that the witnesses didn't have the opportunity to talk to each other before giving their testimony. So their testimony can be considered independent testimony. Okay. And the story they tell are quite similar to one to the other. Then we can conclude that each of the witness is a reliable witness. Just because they didn't have the opportunity to talk before, so to agree on which story to say, okay, and because they give just the same story. Okay. Here, it's clear that witnesses represent a different method of observation, the different experiment by Jean Perrin, okay, that deploy different skills and relying on different theories. Why it doesn't work for economics? Okay. Well, in order to present the opinion by Cartwright, I just mentioned, I don't enter into details, but I just mentioned a case study she uses, one of the case studies she uses, and this case study has to do with this question: how does the changes in wages affect the amount of work effort? Okay, so the problem is that we need to find a relation which is between these two quantities, okay, these two variables. As I told you at the beginning, the repetition here is the implementation of different models in order to establish the relation between these two quantities. In fact, it's something that has been done. And the results are highly variable from a quantitative point of view, but not from a qualitative point of view. So we will see it in a moment. Now I will just report Nancy Cartwright's opinion, but before reading it, I needed to know that E is a quantity that can be used to measure the relation between the two. So we need to understand what Nancy Cartwright said. And we read, the central tendency of estimates of E lies between -0.17 and -0.08. From this, I noted that economists are prone to conclude that E is small and negative. The exact value is unknown, but it is the sign which is the central interest. And these studies taken together give us reasonable evidence about that. That's how the economists think. That's what Nancy Cartwright said. And then she asked, what is the reasoning for such conclusion? She doesn't give an answer to this question. She just makes a negative point. Okay, they don't reason following an IB way of reasoning. They're not using inference to the best explanation. If I have time at the end, I will try. I just try to give a solution to this question. So, why IB doesn't work in this case? Why witnesses in economics are not reliable? She gave 3 different reasons. Maybe there is a 4th one, but I think that these 3 are the most important. The first is that is this one. We cannot be very secure of auxiliary hypotheses we use. Because economics, for the most part, deals with the full complexities of situations. That's what you said. So if we compare what economics do with what physics do, or physics may, that's what Nancy Cartwright said, study an object that is falling in the void, okay, may study situations that are quite isolated, even when they go out of the laboratory. They still comprehend things in this way. But economists can do it. Of course, they can't take into account all the elements, but this is another problem. It's a practical problem. Okay. The second point is that the structure of the reproduction in physics and in economics is substantially different. With this Nancy Cartwright words, Ferran makes different things in order to determine the same quantity. So different experiments to determine the same quantity, the Avogadro number. Okay. While economics do the same things in different ways. They try to understand the relation, but they do it in a different way. The model, in fact, their models, in fact, modelize the same situation. While in Perrin's case, we have different phenomena, different situations. So we can transport the IB way of inference from physics to economics. At least to this way of interpreting reproduction in economics is one of her assumptions. The third point is that even what she said is that even in situations in which we might have even a quantitative results that are similar from a quantitative point of view, okay, that is not a study, we can't conclude that each model is a reliable way of describing that relation. Because each model can be contradictory one to the other, they can be incompatible one to the other, and they might all be wrong. Okay. This is not really clear point. Okay, but this she makes this she confronted in this way physics, the physics case and the economics case. So this is the structure of her arguments. Okay. She said in the end that we never use IDE for reasoning in economics, and so reproduction, as she interprets reproduction, is not a good way of reasoning in economics. Okay, but that's just negative points. At a certain point, she mentioned this famous economist. She doesn't tell us the name. One of his friends, and his friend, this friend of her, commenting the case study, said this: I believe in the correctness of the minus sign. If you remember, E has a minus, okay, is a negative sign. For the same reason, I believe that the lights will go on when I turn the switch. This seems to be just plain numerical induction. I turn the switch 10 times, 100 times, the light goes on, the 100 times and 1, I will turn the switch and the light will go on again. Maybe yes, I don't know, she doesn't comment on it, but I think at this point, it's a point that reinforces what she said, that economics are prone to draw conclusions, so they draw some conclusions. She just gave us with some feeling of dissatisfaction. She just tell what the economists can't do, how they can't think. Okay, but I would like to try to, if I have time, okay, to try to give a small answer to this problem. I know small because I'm not sure about it, and because I think that the explanatory work that the hypothesis makes has to do with the fact that in some way we are prone to draw some conclusions about that hypothesis. Okay, it's only that the IBE strategy is, from a certain point of view, too strong, let's say. Okay, but if we come back to the maybe it's a debatable question. Origin of inference to the best explanation, and especially the writings of Charles Sanders Peirce, we discovered that scholars have recognized that it's possible to distinguish two different but similar inferences under the heading abduction. Nowadays, abduction is used in two ways. One, unfortunately, as a synonymous of inference to the best explanation, and it is not. The other as an umbrella term that include inference to the best explanation on one side and something else on the other. Okay, this something else is the things I will try to rely on for giving an answer to the question. So the first one is the parent, let's say, of inference to the best explanation. Okay, one is the argument that has the function of concluding directly in favor of the truth of the hypothesis. Okay, the hypothesis that make the explanatory work. And this is inference to the best explanation in both versions, the atom version and the witnesses version. The other inference has the function of concluding simply that the hypothesis that is able to explain the data is worth considering as a good hypothesis. So we can plan future research. We can take this hypothesis as a starting point. We don't need to argue that it's possibly true. Okay. We just take it as a starting point for future research. So here the schema is completed. If we use abduction, we can say this is just temperature. We are not entitled to conclude that age is probably true. We're making reproduction experiments. But simply that it is rational to use researchers in order to further investigate age. So let's go back to the case study. The hypothesis might be this one. E, in fact, has minus signs and is small. And we can say that if E were be true, then we could explain why all the experiments, even if different from a quantitative point of view, have a certain qualitative similarity. We can explain that's explanatory work. From this, what is the conclusion that we might draw is that in economics, we don't draw conclusions about the truth of the models or the reliability as tools of measurement. If there is some result that is common to the implementation of different models, we can trust it as a good indication of how further develop our research, construct new models, starting from this. And so we can say, at a certain point, the idea that reproduction is a sort of IB. It's not an IB inference, in fact, but it's something akin to IB. It's abduction. in this ancient sense, as a Charles Augustine. And that's all. I finished. Thank you.
Thank you both. I have the Q&A. Is there a question? Ryan?
Thank you very much. That was really interesting. I like the idea, and I think just you could apply it, I think, also to the kinds of replication stuff we were talking about, because maybe you could say that when you do have successful replications, and this would apply also to the exploratory data analysis, not just the kind of controlled experiment kind of thing. And then you could bring in this Persian notion to say, to give you a sense in which there's a kind of inference to the best explanation going on even in exploratory data, because it's suggesting hypotheses that could be promising.
Yeah.
For future research.
Yeah.
So I like the idea.
Yeah. I don't think you need an answer, but yes, I agree with you. Okay.
This is just a clarification question. So, yeah, I'm just wondering, yeah, the idea of applying this kind of action to the applicability in the card. So, but you say that you cannot say anything about the models.
Sorry?
The models that you use, no? That's what you said.
Yeah, you cannot say that you are reliable or reliable to measure what you want.
So what can you say if we adopt your model for understanding replication or
So if we adopt abduction, you mean?
yeah, the case of the company.
Yes, what I said is that you can say it's simply that, okay, maybe it's better to explain it in going back here. No. Here. This is the classical way in which we present the inference to the best explanation. But in Charles Sanders' writings, the best explanation drops. You don't have this expression. So it sounds very strange because it sounds, we have a certain surprising set of data D. The hypothesis H provides a good explanation for D, hence H is true. Under determination, I mean, we can't separate, okay? And of course, Pierce knows. So why the scholar said maybe he was intending something different with this kind of schema. I'm sorry, yes. Maybe he was intending something different, okay? So the idea is that in the other way, abduction is not the function to argue for the truth of H, but simply for the utility for the, yes, H is useful. Use something you can bet on, something on which you can project new research, something you can take in consideration as a good hypothesis. That's all. Okay.
So you can conclude that in the comments, the reproduction hypothesis
Reproduction only, yes.
At best useful. That's what you want to conclude?
Reproduction, yes, aim at finding useful hypothesis. Yes, that's okay. And some people just trace this distinction, saying using an old-fashioned way, saying that inference to the best explanation is part of the context of justification, while abduction is part of the context of making a hypothesis. Okay, it's the way it is. So yes. And I don't know if we can extrapolate this way of thinking from economics to other kind of sciences, maybe yes, to other scientific fields in which models are more or less used in the same way.
There is, at least in my mind, something more complex. For instance, the last sentence, hence H is true. Probably it's better to say is temporary for this data, not true. From here up to.
Yes, yes, of course.
Next century.
Yes.
And so on.
Yes.
Because this is again the problem of finding the necessity to find a new field or a new model.
Oh, yes, yes, of course,
So
absolutely, yes. But time does not enter into logic relations, so that's the problem here. Of course. Okay. First of all, as I said, it's non-deductive, so we are not certain about the conclusion. We just raise it and it's true. That's all. And for so it might prove to be not a good hypothesis if we get some new data or other things. Yes, of course, absolutely.
any other question? So, again. Next, please. Sandra Salvat.
Thank you, Giuliano.
And
Well, don't worry, now it will appear,
Okay.
but I don't know where it is actually. No, ok, quale storia? Do you know where it is? Ok, sì. Found. Ok, adesso per vedere schermo intero, CTRL F. Anyway, I thank the rest of the organizing committee for this very interesting workshop and summer school that is going on. It's really a nice experience. The gente.
No, è normale. Che succede qua?
Very time worship. At a certain point, there are some technical problems. Unfortunately.
No, perché non posso dare.
Yes. Yes, and every time.
Okay, thank you. Grazie.
Again, so we can start.
I don't know. If you want to say something, it's okay.
Santana, it's a joint with Good work with Luigi Pace, and the title is the replicability and safe on-time target inference. Thanks.
Thank you, Massimiliano. And well, the titles, I think most of you sounds a little bit strange because maybe this safe and time valid inference is something that most of you didn't hear about. Non schermo, non funziona.
Questo qui.
No.
Clicca sullo schermo. Clicca.
Controllo.
No. Sì.
Questo me lo rifaccio.
Okay. Fantastic. Okay, so what's going on in the statistical inference part related to replicability issues? A few years ago, Luigi Pace was hiding there, and I started thinking about this, and we read a lot of papers and started thinking about how one could adjust statistical inference in order to take replicability issues and the desired replicability into account. And just after a while, we discovered that there is a big, let's say, rapidly increasing literature and set of people that is working on similar topics. And so this is the reason for the acronym. We didn't invent it. It's in a paper that I will show you shortly. So it's something. And the ideas, I will just, in this 20 minutes, give you some introductory ideas. But the main points are then the basis of some current research we are doing together with Nicola, who's sitting there, and Claudia. It's not here. Okay, so I guess you have seen this picture before, and that's the National Academy of Science report. So what are the very important interactions between replicability and statistics? So of course, replicability is considered to be the hallmark or maybe gold standard, but for somebody it's just a myth, it depends on how you see it, of science. And of course, when findings are statistical in nature, so there is variability that we recognize as haphazard variability. What counts as a replication of a finding is very subtle. We need a lot. We had a workshop, we had a summer school, and both Brandon and Giovanni spent hours trying to detail what we mean by replicability. So the point, if we remember the definition that Giovanni said, is finding consistent results across studies aimed to answer the same question. So each word, as Giovanni said, of this definition requires a very in-depth analysis. And in particular, what is a replication of an experiment involving randomness? And there are papers. I thank Brandon for pointing out some very relevant literature in the philosophy. So the paper by Masheri is really illuminating about this. And even more problematic is how we assess uncertainty of results and make this, combine this with the idea of finding what I say, the consistency of results. So how do we say that we have consistency of results, and at the same time, how can we take into account that there is uncertainty in the statements we are making on the basis of data? So I will now speak about hypothesis testing, and we concentrate on, estimation of a quantity and the related estimation interval, so from several different points. So we want to estimate a quantity, say an effect size, and we think of the estimation interval. How do we build this? And how can we modify the way we construct it in order to take into account replicability requirements? This is the main point. So this is one of the homework that we were very happy to receive, and this is a paper by Romero on philosophy of science and the replicability crisis on a philosophical journal. And going to the, say, practical side, apart from all the definitions that, as I said, there is a lot of thought and discussion. What to do with device, and this is something that Brandon already illustrated in his seminar, is statistical reforms, methodological reforms, and social reforms. So I will stop on statistical reforms, but Brandon said what we mean about with methodological reforms, like the rules for editorial rules or the pre-registration ideas, open science, and so on. And similar with social reforms. And the first important social reform is education, as I said, and also the reward system for promotions and grants and so on. So going to statistical reforms, what can we do? Sorry. This is from the essentially a paper by Romero, so it's a very quick summary of the points he lists. So of course, attention to replicability requires rethinking statistical procedures. This is obvious. And so we are happy about that because these are very interesting times for people working in statistics and on foundations of statistical inference. Many, you said too many, and we agree, proposals of reform in the literature revolve around p-values and null hypothesis significance testing, which is a difficult, I mean, it's not the right starting point for facing the problem. And the associated the questionable reserve practices, I learned this acronym, which I must confess I didn't know, QRP, questionable reserve practice, like p-hacking and that's similar ideas. And so focusing on p-values is, say, a lost battle from the beginning, because a p-value, I mean, is a statistic, is a random variable. So how can we think we replicate? And it's very difficult to define replicability in terms of p-values, and when they are used as decision rules, the situation is even worse. So a bunch of authors, so there is I don't remember, but it's a huge number of authors in this Benjamin paper, I think 72, if I remember correctly, proposed with some motivation, I mean, very, very eminent, both statisticians, probabilists, philosophers, and economists, to lower the threshold for significance from 0.05 to 0.05. They gave some argument, I will not explain. They gave some argument also for, of agreement between the, say, frequentist and Bayesian reasoning. Anyway, this was a very practical instruction, and this might be a possibility. Or maybe reject the values altogether and embrace Bayesian inference, and this is also a possibility. What can we say about this? Maybe none of these ideas is completely satisfactory. And anyway, none of these falls into what I'm going to briefly talk about, that is this study, that is the acronym of safe anytime valid inference. On the same web page where you find Giovanni's forthcoming paper on the definition of replicability of prediction rule, you will find this paper by Randa, Stromberg, Bock, and Schaeffer on game theoretic statistics and safe anytime valid inference. And this is an extract from the introductory section. So I just underlined the main idea. So we need to go beyond this approval of picking. This is a special point. And we instead should give researchers tools to fully accommodate it. And the branch of mathematical statistics that enables this dates back to the last century and the work on sequential analysis, but actually only a part of sequential analysis, not the whole set of the sequential techniques, and in particular, notably, confidence sequencing and tensor power model. So the rest of the talk, I will concentrate on this idea of confidence sequences, and I also encourage you to have a look at the paper, which is very rich, illustrates many threads of work in this field. So there are many developments. Some of them are really very theoretical, so they're based on martingale theory and difficult stuff. But I try to just focus on what we think is the simplest possible presentation. So the idea is not, this is important, is not like examining separate studies you saw in the presentation of Giovanni. You have study S1, SK. Here the idea is you concentrate on inference with accumulating data, which is the situation that gives rise also to the hacking and stop looking at your data when you have a small inactive value and things like that. So SAVI, sorry for the acronym, I don't like, but it's very long, so I use the full name is too long. So it's concerned with obtaining coherent results of inference when you have accumulating data. And this is not only for replicability studies, but there are many practical situations when you have where you have say, online inference, you have streaming data sets, you have web experiments, which are called A/B testing. So you test one product against another in web experiments or drug surveillance and so on. So what is the point? If you observe data sequentially, if at a certain point you have a, say, the true or a very reliable representation of the truth, you are not happy that you maybe announced something that was in contradiction with this in an earlier stage of the analysis. Think, for instance, when you analyze the result of an election. In an election, the final result is known, so at a certain point, and if you say something that is in contradiction with the final, that's not reputational penalty, as I said before, as I wrote before. Okay, so here we focus on estimation intervals and on those of the simplest possible form, that is an estimate plus or minus some uncertainty measure. Then you can make more complicated. And the idea is for say a scalar quantity, but then you can generalize this. So different forms of uncertainty measures are used with different context and aims. So the point here is, well, how can we make this uncertainty measure to say cope with the replicability requirements? I take say a very simple reference example, but it's not only simple, it's also a kind of basis for more complicated situations. So it's not really just a toy example. So suppose you have independent observations from a normal with no variance, and you want to make an estimation interval for the mean with data. And suppose at stage n, you have observations y1, yn, and you denote the sample mean. And so you can construct the standard confidence interval, say the best known, or for instance, you can construct a Bayesian credible interval using a conjugate prior. And other possibilities, of course, just change the prior or take maybe outside the normal example, other measures of accuracy in the frequentist approach. From a numerical point of view, the two intervals substantially overlap, both when the prior variance is large or when n is large. What I want to say is also that here we think of data coming one at a time, but of course this can be easily extended. I mean, it's the same if you have observations that come in batches, which is more common, of course, in applications, not one at a time. Okay, so this estimation intervals, as many of you know, have very different properties, because the first intervals, IF, F is for frequentist, have a confidence level which refers to the probability that the interval contains mu in a repetition of experiment, and this is the confidence level, while the Bayesian posterior probability is involved in the properties of the credible interval. So the posterior probability that mu belongs is equal to 1 minus alpha. So actually we use the same alpha, but they are completely different interpretations. And this may cause some confusions in people who apply in statistics. Apart from that, if we work in a sequential setting with optional stopping time, optional means that you can decide for whatever reason to finish your observation. We have some deficiencies, problems of this interval. So if we repeat the procedure at various stages, what happens is that the frequentist coverage property, so we focus now on the frequentist properties, because essentially we think that as n diverges numerically, the two kind of constructions are the same, and we will go back to the Bayesian interpretation at the end. So frequentist coverage properties are not satisfied anymore, so the level is not 1 minus alpha anymore. And we can obtain contradictory conclusions with high probability when the sample is enlarged. So you can have a confidence interval at a certain stage, and the intersection with the confidence interval obtained at a later stage is empty. So the two intervals tell you two different, give you two different conclusions. So here is an example. And sorry, the definition is not that sharp, but here, for instance, we consider a situation where mu is equal to 1. So this is somewhere the horizontal line, the true parameter value. And this is how one possible sequence of fixed and confidence intervals might behave. Just to make the situation more macroscopic, we took 1 minus alpha 0.8, which is quite unusual, but it's just because then you see better in the picture what happens. So actually, what happens is that 1 is not contained in many of these intervals, even if you go, I mean, I'm not able to draw a straight line. I'm sorry, we should have made it thicker. But this is more invisible. For instance, the interval you have here, this time, has empty intersection with an interval that you can have at a later stage. So the intersection is empty. And this is just one sequence. If you repeat this in a simulation, the empirical percentage of contradictions and non-coverages are rather impressive, because if you take, these are the usual 1 minus alpha, so you find the usual 0.95, that was at the 95.5%, and you see that the percentages of non-coverages along the sequences are very large and a little bit lower, but you also have a notable percentage of contradictions. So this can be studied analytically, because it's very simple, at least in this case, to show that the probability that two intervals at different sample sizes have an empty intersection is positive, and so along the sequence, the probability will be 1 that you find a contradiction. So although, as you saw, the intervals shrink as n diverges towards the true mean, the problem is that you can have conflicting conclusions at different stages. This was so what are confidence sequences? Actually, this name is not a novelty, because the construction was brilliantly introduced in a paper by Herbert Robbins, the probabilist, in 1970. And the idea is, and we look at the example, then say something more general, but in the normal example, the idea is that in the end, we have anyway an estimation interval, which is of the form estimate plus or minus something, but this something is such that the coverage guarantee is much stronger, in the sense that we have an uncertainty measure that ensures that the probability of coverage along the whole sequence can be bounded below by 1 minus epsilon. So we don't write on purpose 1 minus alpha, because this is a completely different concept. And so we also gave a name, which I don't know if it is used by others, but we call this persistence level. And this is the other very important property that explains the anytime adverb, is that this is guaranteed independently of the stopping rule. So anytime validity means whatever rule you choose for stopping or something, then you have anyway this guarantee. And as a consequence of this control, uniform control, we have also control on the probability of contradiction. So we can see that, we can show that similarly, the probability that the intersection of the intervals forming the sequence, the probability that this intersection is empty, is bounded above by epsilon. So we can make it as small as we want. There are many ways to construct mixture confidence sequences. The theoretical basis is related to an inequality in the Martin theory, which is known as building equality. And you will find the many different proposals of construction in the paper by Randons that I quoted, and this is the reference to building equality that I will show now. And the simplest possible form is for a parametric model, but a lot of the developments are actually non-parametric. Is suppose you have a parameter theta for your model, and it's three-dimensional, and you have densities in your model, which we denote by Pn. And mixture confidence intervals, mixture confidence sequences, sorry, take this form. So they include the theta values such that the density is greater or equal than this is an epsilon, which is almost vanishing, times the integral of the density with respect to some weight function. And whatever the weight function is, provided it is a probability density over theta, the procedure has the properties that they told you. So if you do this in the normal example and you take a conjugate mixing weight function, it could be a prior if you think it in a Bayesian way. But anyway, this also it's not a prior necessarily, it's just a weight function if you want a frequency interpretation. And in that case, you can obtain also a very simple closed form expression, which we don't give, and you can find in the references. So here is, again, I'm sorry that this line here is the same situation as before. And we compare the original, the frequentist intervals, the sequence of frequentist fixed time intervals with the confidence sequence. So all the phenomena of non-coverage in this special, I mean, is this just one instance, but the probability guarantee is over the set of all possible sequences. You see that you don't have in this case contradictions, and actually you don't have also non-coverages, which I mean does not happen with probability 1, but happens with the controlled probability, which is the result. There is something hidden here, but anyway, just to I don't know if I have time. I think 3 minutes. Yeah. Okay, just as a say complementary evaluation, the nice thing we found about this mixture confidence sequences is that they are in line with many views of inference. So they were presented here as from a frequentist point of view, but actually they have a Bayesian interpretation and they have also an evidential interpretation. So, and they are coherent, they are among the rare examples of procedures which have a frequentist interpretation, and they are also in line with the strong likelihood principle for those who are familiar with this, and that as well with the sufficiency and conditionality. So, of course, if you have prior information, you can use it to as a weight function, and using with the usual notation for the posterior, P of theta given Y, so this is the posterior density, the form, so exactly the same expression can be rewritten in this form. And so you just plug in the ingredients, and the confidence sequence can be read in terms of prior and posterior, in the sense that you included the theta value such that the posterior is greater or equal than a fraction of the prior, which is not the usual credible interval. It's something different, but it's not new, because we found, for instance, that Evans, Michael Evans, the statistician in Toronto, has been working a lot on this. He has a book on this relative belief ratio and how to construct confidence statements, say, based on that. This is just for the, for the formula, but what are the properties? The properties are also simply derived from the structure of the mixture confidence sequence, and is that actually for fixed n. So if you look at this, the construction with fixed n, because of course if you do posterior probability, you have to condition on the data. So you condition on a specific n. The credibility level of the confidence sequence is anyway at least 1 minus epsilon. So this 1 minus epsilon is a lower bound quantifying, say, the error both in a frequentist and in a Bayesian sense. And so I think this is a good point. And unlike what happens with the usual, for the usual 1 minus alpha credible intervals, we can also evaluate the Bayesian probability of non-contradiction. Of course, this cannot be done anymore conditional on data, so we have to work with a joint distribution of theta and y. And with respect to this joint distribution, again, we find that the probability of non-contradiction is bounded is at least 1 minus epsilon, so the same bound. Looks like a different epsilon, but it's the same. To close mixture confidence sequences, there also what is called an evidential interpretation, and this is a recent paper by Morgan, Marquez, and co-authors. And indeed, again, it is based on a ratio which can be easily recognized as a Bayes factor, and so the interval can also be read without, of course, probability evaluations in terms of the evidential construction. And so this is the idea. So to summarize, we try to introduce confidence sequences and replicability as controlled probability of non-contradiction. So this is a replicability not in the sense of having a series of studies, but in the sense of having coherent conclusions when you have accumulating data. And then we underline, saying what we think is an advantage of mixture confidence sequences, that is that they are coherent with many points of view in statistical inference. There are a lot of generalizations. There is a very advanced theory behind the generalizations. So the paper by Randall and other authors that I showed you in the beginning, they consider non-parametric settings, they analyze robustness, dependence, and the other paper on Yanas by Howard and other authors has specifically to do with non-parametric confidence sequence. And very interesting for application, the situation where your estimate varies with time, so with n in this case, because that can be constructed with n. Just to go to tell you briefly what we are working on. We are not the only ones actually, because there is a paper by Wally Smith on this. We can also think about approximations for confidence sequences. So using, say, normal approximations, the usual ones, but in this setting. And then you can extend it to various situations such as pseudo-likelihood. It's something we have been done. Currently, we're actually working on computational aspects when you have streaming data sets, how, if the model is not the basic one, you can update estimates in an efficient way, and how you can update the variability measure to construct the sequence. And this is the ongoing. Okay, so we finished here. If anybody's interested, here are some references. The talk, questions,
Yes.
Oh, thanks so much. That was great. Do you guys have like barcode and stuff for calculating these things in case there's?
Yeah, I mean.
You got that? Yeah, 'cause I was hoping.
You have to talk with him.
No, I was hoping because I wanna like add this to the.
No, we can be.
to the study.
I mean, it's not, I mean, I don't think we have published it. We can make it available.
Yeah.
No problem. No, I'm joking, but he's the very computational member of the group.
So the first one is thanks, Alexandra. So just 2 points. The first one is if you can go back to the construction of the sequence. So it's always symmetric, or can it?
No. Can be. I mean, if you look at this from a likelihood point of view, it's like a likelihood.
Yeah, it's a symmetry, so can come off from.
No, I mean the normal case. The normal case has this structure, but in general you don't have.
Yeah, I was wondering like which factor gives, if you go like to the previous slide, so which factor gives more structure to the
which one? You mean below? This one.
Yeah, this one. So can also the weight induce the probability? So for both steps.
No, but of course, this is a likelihood, so.
And second point, whether, so I know that testing was not for the part.
But of course, there is the dual version of this.
And this can be done, so what is the most challenging part by like inverting this to construct test?
No, actually directly by the construction of, by building a quality, you can have a test that
Like the
control
direct-
probability and
Nice.
test the construction.
Okay, thanks.
Any other question, please?
Thank you. This was really insightful and gives me a lot to think about. I'm particularly fascinated by how it falls into the same formal framework, the replicability and the way we learn sequentially from experiments in cumulative ways, you know, talking a lot about it, like we do meta-analysis and replicability and, you know, which one of the two should be on the other. This is a very elegant way. Think about both at the same time. The only quibble I have is one of terminology. I thought that Bayesian updating was the only part of my life that was free of contradiction. And you're really pushing me over the edge.
Well, it depends on where you wait. I mean,
Right,
if you
so-
wait along the sequence, you can have a
So I
Bayesian
agree
wheel.
that those different intervals, if you are defining replicability as reaching the same conclusion based on the confidence interval at different stage are ugly. But at least from a Bayesian standpoint, I think defining them as contradiction is a little bit of a harsh piece of terminology for two reasons. One is that there are intervals that reflect the probability distribution. So the Bayesian statement is not that with certainty the parameters in that interval is that the parameters in that interval with probability X%. And if you make that X small enough,
Yeah,
I make a contradiction at every step.
yeah.
The second reason why hopefully it's not a contradiction is because they're conditioning on two different sets of events, right? So I'm allowed to have different opinions after I see different data. So probably too late to choose a different term, but I just thought I'd bring this up. Other than that, it's really
I mean, yeah, we just think of it numerically. I mean, if you give the numbers, you obtain an intersection. So the user is not happy about this.
But in a strict definition of replicability, where you define
This is not a strict
replicability to
definition,
be-
it's our own
to be,
definition.
based on the overlap of the confidence interval, then I really get what you're saying. I get the connection between replicability and it is very helpful. So,
Thank you.
Any other question? So, no questions? Thanks again. Adesso vediamo se riusciamo a trovare la tua. Forse tu sei più bravo di me. Io per casina. Chiudo la mia. Vado qua. Ti riconosci?
Perfetto, sì, quella grazie.
Questa qua?
Sì, sì.
Adesso però il control qualcosa.
Sì, sì, mi arrendo. Yes. So I'm the last speaker and I think.
This is Gianmarco Alcoe.
Yes.
Yeah, the Department of Developmental Social Psychology. The title of the talk is the crisis. It's not the only one. Other more challenges, opportunities to science. We are a little bit late now. This program thing.
Thank you very much. So first, I would like to thank the organizer for inviting me to these two amazing and interdisciplinary events like the summer school and also the workshop of today. And as you may say, after the discussion of today, maybe you could reasonably say that there's a replicability crisis, but I can guarantee that it's not. There are also other prizes that today we will discuss. So first, I want to give you, let me put this. Maybe, well, I don't know. No. Lo rimetto su per me.
Nascondi i controlli che ognuno di
Nascondi.
sopra. Ecco.
Oh, super. So first I will give you two premises just to make clear what I will talk about and what I will not talk about. So let's start with the first premise, and I recall you with the traditional categorization of the exploratory research when you explore data and use a result to generate hypotheses. As opposed to confirmatory research when you are pre-planned formalized hypothesis and you test hypothesis. Of course, why it doesn't work? Okay, so thank you. So of course, exploratory and confirmatory research are complementary. And usually we start with exploratory research, and based on findings from exploratory research, we move to confirmatory research. Both kinds of research are most important. I love exploratory research personally, but indeed, as Tukey, that is the father of exploratory data analysis, stated, finding the question is often more important than finding the answer. So both are important. With regard to the replication crisis, and in particularly with regard to confirmatory research, we could say that bad science could be viewed as presenting exploratory findings as confirmatory conclusions, whereas good science is, in the case of confirmatory research, is presenting confirmatory conclusion, but based on prepared hypothesis. This is important, and you have to be transparent about that. So in this talk, I will focus on confirmatory research, just to make things clear. The other premise is that I will use psychology as a motivating case for this reason. Replicability crisis started examining psychological and medical papers. Psychological science was among the first to introduce potential remedies, such as an emphasis on open science, on the need to do replication studies and pre-registration. Lastly, in the past 5 years, at least 2 more crises have emerged in psychological research, but these crises are pervasive across all scientific disciplines. So in theory, and here we have our Galileo Galilei, in theory, how to conduct confirmatory research is clear. You based on theory and based on, for example, exploratory findings, you formulate and formalize hypotheses, you identify the relevant variable, and importantly, how to measure them. You plan your research design, sample size, and you prepare statistical analysis. And this is the first part, the first big step. After that, in a confirmatory perspective, only after that, you collect data, you test your hypothesis, and interpret and share your result. It seems not so difficult, but in practice, a lot of bad things will happen, as Brandon presents. So we have the so-called QRPs, the questionable research practices, and we have a lot of kind of questionable research practices for all tastes. We discussed some of this today, so basically all. And I think one of the more important is and relevant is asking, so hypothesizing after results are known. And interestingly, Alessandra suggests us a way to deal with stopping collecting data before or after the planning of the sample. Okay, I will also not talk about fraud because it's not because it's not done, but I think it's another kind of another questionable research practice. It's not so questionable at least. And one remedy, as we discussed today, to move toward a more rigorous science is the pre-registration. In particular, pre-registration means to use registered records, which some of you may know, and are a new kind of scientific paper that were born in 2013. And we have two stages. It's different from the traditional paper, but we have two stages. In the first stage, you develop the idea and you pre-plan your design, including all the statistical analysis. And here you have the review. So you submit your paper, and here you have a first review. After all the issues are fixed, you can go on. And at this stage, you have a so-called in principle acceptance of the work. Then you collect data, you analyze them, and you write the report. And you have the stage 2, which is basically very fast because it's there to check that what was said here is done. So after that, you can publish. And the idea is that because the study is accepted in advance, so here the incentives for author change from producing the most beautiful story to the more accurate one. And with regard to what Brandon said, there is evidence here, increasing evidence that this kind of paper are making things better, in particular reducing publication bias. Because here, so the problem of positive or negative result is irrelevant basically, because the acceptance is zero. But what about other recent crises and maybe other schools? So let's focus on three main aspects of confirmatory research, these three. And for each of these aspects, there is currently evidence of a crisis. So the crisis of the school, about we discussed in the school, so the replication of star crisis that officially started with the paper, famous paper of Ioannidis, why most published research partner was. We have the so-called validation crisis. The third paper could be this of Shima in 2021, and also the so-called theory crisis. And then we will see in detail what these two crises are. So the theory and the validation crisis. An important note is that these crises are not new. Since 1970, there have been many articles about them. However, these articles have had little impact on the scientific community. So this is just the first paper in the field of psychology called the validation crisis, which is recent, is 2021. This is another interesting paper, and here we find interesting things called questionable measurement practices, as opposed to questionable research practice. So a kind of list. And the idea is simple. So in the case of psychology, psychometrically invalid, but more in general, invalid measurements imply invalid and unreplicable result. So if you have this kind of issue with the measurements and how you measure your variable, it's also strange to think about replicating a study because there's a problem before replicating. The instruments are not good. Here is an example, another study from 2022. So this is a review of 100 studies published in 3 leading journals of psychology during 2008. And the main results are that of around 200 scales used to measure the variable of interest, only the 30% were reported with their citation to the associated validation study. There is a surprising evidence that issues related to validity were mostly neglected, and strong evidence for poor psychometric property of the measure used. So these are the main of the measurement slides. This is the theory crisis. So also here we have a kind of official paper, and is 2021 theory crisis in psychology. And this is another interesting paper that talk about the problem of linking theory to statistical model in a particular field. So it's related to theory and factor analysis and network analysis. So the main ingredients of the theory crisis is there is evidence for vague and not testable theories, lack of mathematical formalization of hypotheses. Maybe in psychology we have a lot of problem with this. So, and a mismatch between theoretical and statistical models. 2 examples, so I will read them because it's so small. So the first guy on the left say this study say massage improve sleep compared to the control group. The other guy say that's awesome. How much longer did the massage group sleep? And the other say 47 seconds per night. So not a big result. So from a theoretical perspective, we could think that this kind of findings or interpretation comes from a bad hypothesis, a vague hypothesis, where kind of the treatment has an effect, which is too narrative, not testable. A more sound hypothesis from a theoretical perspective should be that the treatment has a specified and clinically relevant effect. Another example is this. Let's suppose that y is our dependent variable, whereas x1, x2, and x3 are our independent variable. But there are some relationship between the independent variables. They are not on the same level. So if we formalize the model in this way, we have a poor formalization of the theoretical model. And consequently, in this case, if we run a linear regression, we will have invalid result based on a not well formalized theoretical model. Whereas in this case, all the relationship between the independent variable are well formalized, precisely formalized. And so we have a good formalization. And in this case, a good way to approach this kind of theoretical model is using structural equation model. So you could have more valid results. So I propose some remedies, also based on my experience on the literature on this and based on this book. So one is for statistician. I think that a statistician should know at least the basic of philosophy of science is to better understand all the scientific process and also measurement theory. So how to link abstract concepts such as well-being to observable indicators, and it's not easy. So I think practically that this should be two kind of mandatory courses in the CV of the statistician. These are some hot techniques that are used, and the use is increased after the replicability crisis as a remedy. So structural equation models that are not new, of course, they are from the 70s. Causal inference and multiverse analysis. Just in a few words, multiverse analysis means present all the analysis you have done, and not only one analysis. So you have a better sense regarding the uncertainty of result. And also, but here in Padua, I know that the things are very good. Statisticians should be trained to work with other scientists. This is fundamental. I propose also some remedy for in a multidisciplinary perspective. So I think that scientists, as you know, statistics is kind of omnipresent in science. So I think that scientists should know at least the basic of statistical reasoning, which in few words means deal with data variation and chance to better communicate with statisticians. And lastly, and I think the most important message of my talk is that experts in the study phenomenon and statistician must collaborate, as we are doing here, from the beginning. But the most important thing is before data are collected. Because you know Fisher, what Fisher primarily said about that. So before data are collected, pre-planning the study before, and not contact or work with the statistician after the damage are done, basically. And so I conclude, and I hope that together we can replace the word crisis with the word renaissance. So thank you very much.
Question? Comments?
I have a question and a comment. The question is whether you're aware of anybody having replicated Ioannidis' statement.
I know that there are a lot of, there are a lot of paper. One famous is of Goodman that is that criticizes something about the Ioannidis paper, but if the Ioannidis paper is in part based on observed data, and on the other side is based on simulation. So if things are going like that, we will have a lot of problems. But I think no one replicate this. I know that Ioannidis, it's a famous thing that during the COVID area, in the beginning, she said that COVID was based on his study was little things, whereas it was not so, and so he was criticized a lot because his research findings were false.
Well, that's an issue of undisclosed confidence, but I don't want to get to the fraud side. I just want to get to a suspicion that I had long before that Ioannidis might be a descendant of this other Greek guy named Zeno who lived in Crete and who a long time ago allegedly said that all Cretans are liars. And there's only sort of a probabilistic version here in play, and one makes some statement about all, 50% of medical results in the medical literature are false, and he makes that statement as a medical researcher publishing in a medical journal. There's simply a 50% probability that that statement is false if his paper is correct. So I think that we should keep that in mind and apply rigorous standards to these papers who are, cry wolf about the price, just as we apply them to all the other important findings that we use to kind of direct scientific research. Problem is that when people self-appoint themselves into this role of being the Grillo Parlante of the situation, it becomes really intimidating to go against them. They have a lot of leverage, a lot of power in social media, and it's a tricky situation to protect the scientific community from potentially overblown claims of unreliability. That's what the common part.
I completely agree, and I think that the Ioannidis paper gives us some insight, but is not a kind of test of science like a Bible. It's something good to take inspiration, but he has some problem.
I have those in psychology that is very interesting that older faculty see a paper given by a student. They are conclusion let's change it, let's make a nice narrative. So you go back and the previous theory was changed, the previous and usually goes so you make a good narrative. This unfortunately should not happen anymore, and thanks to pre-registration. So even though pre-registration is not perfect,
yes,
no, there are also some limitations, but at least will not turn, some exploratory kind of work into fake.
yes, I completely agree, and I want to say that pre-registration is important from a practical viewpoint, but also from a more theoretical point of view. So what pre-registration is to kind of make some discipline in science. So to check things. Of course, pre-registration is not the panacea of everything, but a good tool.
So thanks again.
Thank you.
Two last things. The first one is to thank again the organizer, specifically the organizer who is not here. So Fabio, but it's probably connected with us. There's a lot of time to organize important they cannot hear, so thanks, Fabio. And secondly, there is a door behind you, and if you take this door and you follow the corridor, you find the stairs. Go down the stairs, you are at the atrium of this building, and there is some streets and some other stuff for you that finish the workshop with something to drink and to. So please keep this door, even if it's written that is alarm, is false.
Riprendo il mio attrezzo qua, grazie.
Questo no, c'è anche il computer, lo porti via.